So we are in the middle of proving the Brooks theorem. More generally, we are proving this least extension of Brooks theorem. As long as G is a connected graph, G is not a complete graph or all cycle, and its least chromatic number is at most its maximum degree. For that, we define this concept of degree choosability, where a graph is degree choosable if the list satisfies that each vertex and list the degree many colors are available, then it is L-colorable. Then the graph is called degree choosable. For that, we first prove this lemma, that if a list is given, and then that list give you more than the degree many colors, that at least one vertex, and then less of them, as many as degree many colors available at that vertex, then it is L-colorable. And also the second one is that if we have a two connected graph satisfying this condition, and some two lists are different, then it is L-colorable. And also we show that if a connected graph G has a degree choosable induced subgraph, then it is degree choosable. So this is the lemma which is useful for us to prove certain graph is degree choosable. Then our strategy is that we want to show a certain graph G is degree choosable, which will be useful for us to prove the Brooks theorem. And for that, we have to show that it has the induced subgraph, which is the degree choosable. And then what would be that subgraph? And we'll show that following graph is degree choosable, where an even cycle with at most one chord is degree choosable. So this is one of the graph with one of the most simplest structure graph that we can think of. And what's this chord? So we define a chord of a cycle is an touch which is not in the cycle, whose endpoints are in the cycle. For example, if you have some cycle, say this set is a chord, or this set is a chord, this is a chord, this is a chord, this is a chord. So this even cycle with at most one chord. So this is induced subgraph. If you take this vertices and then you take the induced subgraph, and number of chords is at most one. It's either 0 or 1, and it is degree choosable. This is not difficult to check. Let H be such a graph, even cycle with at most one chord, then it is two connected. It's easy to check that this is two connected. It's a cycle. Cycle is two connected, and you add 1 or 0 edges, so it is two connected. Let's say you have a L, your list assignment. Such that arrow B is a list aside a list degree. Then we can consider two cases. If the list are not identical. And it is two connected, so the B in the previous lemma, this one applies. Then this shows that this is L colorable. It implies that it is L colorable. So you can choose proper coloring. If not, if the lists are identical, then what happens? Then this L coloring is just the proper coloring. So we can use the two colors if H has no chord. And it's just an even cycle, so you can two color. And use three colors if H has a chord. Then if you have an even cycle with one chord, then it's easy to check that it is three colors. So in either case, it is L colorable, and that was for all such L. Thus, H is degree choosable. So this graph is degree choosable. Then now we want to show that we can find such a graph in a given graph as long as it satisfies certain condition. And what's the condition? So we can prove this in a triangle free graph. Which has at least one even cycle. The shortest even cycle has at most one chord. Why do we care about this triangle free graph with at least one even cycle? You will see later. After proving this lemma, we will consider some graph which is two connected but not complete graph or not all cycle. We want to show that it has even cycle with at most one chord, unless it is triangle free. So as long as it has triangle, then we will show that it has an even cycle with at most one chord. Then in the remaining cases, the triangle free case, which this lemma will take care of it. So with that foresight, we prove this lemma first. Let's say C is the shortest even cycle. Then what happens? This is your C. Then what? If it doesn't have any chord, then you're done. This is a even cycle has zero chord. And if it has chord, the end points of any chord of this C are separated by even distance along C. What does it mean? If you have this vertex, this is the length 1, 2, 3, and this is the chord, then it's a contradiction because this one is shorter even cycle than C. C is shortest even cycle. There are no even cycle which is shorter than this. But if this chord, the distance between them is odd, then this odd number of edges together with this chord give you a shorter even cycle. So chord is something like this. Distance between this is even, this is even. So even if you take this, it's shorter cycle but odd cycle. This is shorter cycle but odd cycle. So it's not contradiction in that case. Okay. So if we have two such cycle, two such chords, then you have two cases. Either two chords looks like this or two chords looks like this. This is a crossing case. This is non-crossing case. And whether they cross or not, two such chords will the cycle shorter than C using two passes on C that have equal parity lesser and so in the chords. Meaning that what? This and this what have according to this length is even, this length is even. So total length is even. So if you delete this, then this and this have the same parity. Because this plus this plus this plus this is even. We already know this two is even, so sum of these two is even. So it's either even, or odd. But what's this? This has shorter length than the entire cycle. So this is shorter even cycle, which is a contradiction. Here, again, you take this. You know that this length is even, this length is even. So if this has certain parity, the even parity, then this is even. If this is odd, then this is odd. So these two have the same parity. So this together, this two is even cycle. But the problem is whether this is shorter or not. In the crossing case, the new cycle might have the same length as before. Namely, if this is just, in this case, this cycle has length 8, and this cycle also have length 8. So we don't get the contradiction yet, right? However, in that case, we can take this cycle, which is shorter, right? Then, the other choice gives us a shorter cycle. Why? Because G is triangle P. Meaning that why do we know that this choice is shorter? If you have this, if this is just an edge, this is just an edge, then this cycle is shorter than, the other cycle. Okay, so what I mean is that if this is not shorter than the other cycle, then the other cycle must have length 4, meaning that this is length 1. In that case, this is K4, which contains triangle. So triangle free means that this is not just length 1 H. This is path with the length, longer path. This is path with the longer length. So this contradicts the minimality of this shortest given cycle. So, and conclusion is C has at most one chord. So now we are almost ready. So we prove this lemma by Erdős, Rubin, Taylor. And they proved the Brooks theorem for two connected graphs. Every two connected graph G, okay, I will say this Brooks theorem is about the degree choosability for two connected graphs. That is not a complete graph or an odd cycle. It contains an even cycle with at most one chord. So this, they show that every two connected graph that is not a complete graph or an odd cycle contains this even cycle with at most one chord. This is in this subgraph, which is degree choosable. We imply that the G itself is a degree choosable graph, which will be an important piece for the proof of Brooks theorem. So how do we show? Let's say you take a Q, the largest clique in G. Why is it useful? If Q has the largest clique, and no matter what vertex you take outside, there is at least one non-neighbor in here. If this vertex is adjacent to every vertex in Q, then you would have added to Q to obtain a bigger clique. That didn't happen, so that means it has at least one non-neighbor there. Using that, I mean, that's useful for us to obtain a cycle with small number of chords. So, since G is not complete, this is not a complete graph. That means it is not Q is not entire, I mean, vertices in G. It has a vertex outside. So you have a vertex here. And since G is still connected, what do you know? Using Menger's theorem, there are independent paths from this vertex to distinct vertices in Q. So there are, you can find the path and path which are independent. So this structure exists. That means we may choose the one such thing which is short. Shortest path P that has endpoints in Q, say U and P. And also it has at least one vertex outside Q. Say, let's say this vertex is X. Okay. let L be the length of this path. Then what happens? If L is 2, then you have U, V, you have X. As I mentioned, there are at least one non-neighbor of X, which is Y. Then this U, X, V, Y forms a 4 cycle of length 4 with one chord where Y is a non-neighbor of X in Q, which is guaranteed by a maximality of Q. Okay. So, otherwise, what do we? If L is L3, we know that every vertex outside Q has at most one neighbor in Q. Because how did we choose? This one was the shortest path. And if there is one vertex sending 2 edges, then that would have given already this situation. Tested P has minimum length. What do you know? Its internal vertex have no neighbor in Q except the other end edges. Meaning that if you have Q and then you have U, you have V, you have this P, these vertices don't have any edges inside of here. If there is an edge, then we might have taken a shorter path. This also doesn't have an other end, neighbor. This has only this neighbor and then not other. This has only this neighbor, not other neighbor. Because otherwise you would have chosen a shorter path. So if this L is odd, then you add edges between U and V. To this path, then this completes chordless even cycle without any chords. So this does not have a chord. If it has chord, then you find the shorter path connecting these two, which is contradiction to the shortestness of this. So this is okay. If L is even, and furthermore there exists Y in UV. So as long as you have Y, which is not U and V, then adding U, Y, V completes an even cycle with one chord. Only chord is UV. Again, this doesn't send any edges to other Y's, and there are no chords inside of here. So this is an even cycle with one chord. What's the only remaining case? The only remaining case is that this Y doesn't exist, meaning that the biggest clique Q consists of only 2 vertices, so that the G is triangle free. And we have a chordless odd cycle. So this is the odd cycle. Yeah. Then what? As we assume that the G is not a complete graph for all cycle, so what do we know by hypothesis? G is, say, this called the all cycle C. G is not C, meaning that G has vertex G outside C. Now what do you know? You have a all cycle, you have G. Now two connectedness of G gives us a shortest path through G. So we can find again path here with the endpoints A and B. Then what do we know? You have this path, this path, this path. So including the AB paths along C, which is this path and this path. We have three independent paths which connects A and B in G. So by P-journal, two of these three have the lengths of the same parity. And it forms an even cycle. So what did we show? It has at least one even cycle. Then what was the previous lemma? Previous lemma said that if you have a triangle free graph with at least one even cycle, and shortest even cycle at the most one chord. So we just show that this is a triangle free graph with at least one even cycle. Hence, the previous lemma implies that G has an even cycle with almost one chord. Now we are very close. We can prove this theorem, which is almost as strong as Brooks' theorem. So if you have a connected graph, G, if it is not degree choosable, then every block of G is a complete graph or an all cycle. So let's say E is a block of G which is not a complete graph or an odd cycle. Assume that such a thing exists, and we want to show that G is degree choosable. For that, we only need to show that it has an induced subgraph which is degree choosable. For that, we only have to show that it has an even cycle with almost one chord. As this B is a block. Block is either one vertex or an edge, or a two connected subgraph. But the one vertex or a single edge is complete graph. And then we just assume that the G is not a complete graph. So you may assume that A is two connecting. And what was the previous theorem? Previous theorem says that it is a two connecting graph that is not complete graph or row cycle. It has a E as a subgraph H. That is an even cycle with almost one chord. And this is an induced subgraph that is degree choosable. So she is degree choosable. Which is a contradiction as we assume that the G is not degree choosable. So that shows that every block of if G has at least one block, which is not a complete graph or old cycle, then it is degree choosable. Now we can prove the group theorem. Actually, the list extension of it. So, but suppose least chromatic number of G is bigger than its degree. Then what do we know? This implies that G is not delta of G minus 1 degenerate. As G is connected graph, if you have a connected graph, if you have one vertex which is smaller than, whose degree is smaller than delta minus 1, then you delete it. And there must be another vertex which was adjacent. Now that has a lower degree, so you can delete it, you can keep delete, you can keep delete it. That means this is delta of G minus 1 degenerate. The only case that this is not delta minus 1 degenerate is that it has a, it is a delta regular. Okay, maybe, let me write it this way. Hence, G has a subgraph H with minimum degree at least delta of G. Otherwise, this is delta minus 1 degenerate. Thus, H is delta of G regular. And since G is connected, and the vertices with degree delta of G in H have no neighbors outside H. We must have that H is same as G. So G itself is delta plus 1. Delta of G. So G is delta of G regular. Then what do we know? Then this is delta. So every vertex has delta of G LR. So if it is degree choosable, then it is delta least colorable. But we assume that this is not. it means that the G is not degree choosable. Then the previous theorem implies that every block of C is either complete graph or an odd cycle. And if G has at least two blocks, then what happens? You have this block. If you have a block, you have this block point graph, which is a forest. In other words, you can draw this block in a tree-like manner. And in this block point graph, there must be a block which corresponds to the leaf. And that's called the leaf block. And if it has at least two blocks, then there must be a leaf block. And this leaf block has this cut vertex, which belongs to another leaf block. Then what happens? Since the cut vertex in a leaf block, it have higher degree than the other vertices in the leaf block. What it means is that you have leaf block and then you have this cut vertex, which stands at least one edge outside. Inside, you have, say, three edges, and then here also three edges. We know that this block is either complete graph or odd cyclic. So in here, this vertex and this vertex have same degree. However, this vertex is cut vertex, so it sends one edge outside, and this two has a different degree. Hence, she has only one block, and she is either complete graph or an odd cycle, which finishes the proof. So this shows that among the connected graph, only graph which requires delta plus one colors in list coloring are the complete graphs and odd cycle. Every other thing you can list color it with maximum degree delta of G colors, which list chromatic number is at most delta of G. Okay, so we have shown this Brooks theorem, and we introduced this concept of list coloring, which is useful and which is more general than the just proper color. Okay, and next time we will learn about edge coloring of graph. So far we have only considered coloring of the vertices, but you might also want to color the edges when you give some special meaning on the pairwise relationship. So edges between two vertices are the relationship. You might want to keep some special meaning on that. Then, sometimes those kind of problems can be modeled using edge coloring. That's what we will learn about in next time. Okay, thank you for listening. I will see you next time.